Now that we know that we really need to look at three variables when we're measuring a gas, pressure, volume, and temperature, it's time to start looking at all of these variables and how they affect each other. Well, unfortunately, as in any decent experiment, we can't test three things at the same time. We can only change one variable, and we can only monitor how one other variable is changing. So we're actually going to have to do three series of experiments to test how all three of these variables are interconnected, when only testing two of them at a time. So for this first set of experiments, we're going to take a look at the relationship between pressure versus volume. And what that means is we're going to have to hold temperature constant. So here's our little experiment. We're going to have some particles moving around in a box, and the temperature here is going to be held constant. Now remember that we see temperature as the speed of the actual molecules, the kinetic energy of the molecules in the box. And what we're physically going to do is to change the volume of the inside of this syringe by kind of plunging it down. So let's set our little molecules off on motion. And what I want you to watch is how frequently those little particles actually strike the sides of the container, because that's how we see pressure. And check out what's happening to our pressure gauge as we decrease our volume. And again, notice those particles are moving just as fast as they were in the beginning, but now they just have less space to move around in, so they're going to be bumping against the sides of the container much, much, much more frequently. One more way to kind of look at this would be with this extra little kind of visualization. So with this one, you can actually see that the volume and the pressure here are changing. And as the volume and the pressure are changing, you can see a graph at the side actually being populated. And it looks as though as the volume is going down, the pressure is going up. And vice versa, as the volume is going back up, the pressure is going down. Now that type of relationship is not direct, it is inverse. And because of that, we can actually now describe it mathematically through two different equations. This first one isn't really going to be used by us mathematically for any kind of calculations, but it's a nice thing to know that pressure times volume, in this case, tends to remain constant. But with that being said, we can actually develop a much more powerful calculation, a much more powerful equation, and that's this one here, under changing conditions. So the original pressure and volume of any gas will also equal a second set of conditions, pressure times volume, as long as it's the same set of gas. This relationship is known as Boyle's law. Boyle's law holds temperature constant and looks at the relationship between pressure and volume. Pressure and volume are inversely related. That means that as pressure goes up, volume goes down. Let's take a look at a sample problem. A sample of a gas has a pressure of 1.5 atm and a volume of 2.5 liters. If the sample is compressed to a new volume of 2.0 liters, what is the new pressure? So now, in this particular problem, although it doesn't specifically say anything about temperature, we can assume that temperature is being held constant. That means we can apply Boyle's law, which is the equation P1V1 equals P2V2. The original pressure times the volume equals the final pressure times the volume. Next step in this problem is to identify the variables. I'm going to kind of scan the problem for just the important numbers here. The first thing that I see is 1.5 atm. Because it's the first pressure that I see in the problem, I'm going to define that as P1. The next number that I see is 2.5 liters. And since that's the first volume that I see in the problem, I'll identify it as V1. Then I see 2.0 liters. That's the second volume in the problem, so I'll identify that as V2. And then finally, the problem is asking me for a new final P2 pressure, and I'll define that as X. Now all that's left is to plug in these variables into the equation, and then to solve for X. With only two significant figures, my final answer is 1.9 atm. Probably a good idea to have a real-life example of what Boyle's law is actually all about. And the thing that comes to my mind would be in scuba diving, you can actually have a condition known as decompression sickness, or the bends. The next video will actually get you a little bit more insight into this specific condition.